Hi, my name is Wenli Chen, and I'm part of April Lab at Zhejiang University. This video presents our AM 2020 paper, Collision-Free Trajectory Planning for Autonomous Surface Vehicle. The other authors of this paper are Yan Jiaqing, Yang Xuemeng, Liu Yong, and Gu Yong. First, let's talk about the motivations of this paper. Autonomous surface vehicles, also known for ASVs, has sparked off more and more concern in the realm of robotics because they meet demands of unmanned, technical, reasonable multi-missions. However, when it comes to trajectory planning on ASVs, there are some critical issues that previous researchers didn't consider or solve. First, ASV performs worse than autonomous cars in maneuverability. The traditional graph-based or sampling-based path searching methods output position-only paths. It makes ASVs hard, even impossible, to follow those jerky and sharp-turn paths. Second, although plenty of works on ASV trajectory planning have been proposed, previous researchers seldom focused on situations that contain obstacles in planning areas. They also rarely perform generated trajectories in simulation or field experiments. Also, ASV carrying limited fuel when performing missions. Energy costs should play an unignorable role in trajectory planning. We use an under-actuated ASV module in this paper. Its prototype is a battery-operated boat with two propeller engines. The equation 1 demonstrates the kinodynamic equation of ASV module. Eta denotes pose vector. X and Y are Earth-fixed reference frame coordinates, and phi represents the angle from the Earth-fixed frame to body reference frame. Nu denotes velocity vector, with U and V are surge and sway velocity, and R is the yaw rate. R phi is a rotation transform matrix from body fixed reference frame to Earth fixed reference frame. M is the inertial matrix. C nu denotes a centripetal matrix, and D nu denotes the damping matrix. C nu and D nu, these two matrices are more important in ASV than autonomous car. For under-actuated ASV model discussed in this paper, two motor struts are unable to provide direct control in sway velocity. Thus, tau u equals F1 plus F2, and tau v equals 0. For the final trajectory, the state variable x contains position, velocity, and acceleration. Tau denotes the control inputs for ASV. The planning method we proposed in this paper is a two-stage framework. The front end is path searching. It produces sequential collision-free waypoints in environments with obstacles. The back end is trajectory generation. It uses the waypoints to generate smooth trajectories, accounting for kinodynamic constraints and state constraints. We use RG star as the front-end path searching planner. However, some of the waypoints are redundant and can be trimmed for the sake of back-end computational time. The method we use for trimming waypoint is simple. One waypoint is redundant if the trajectory, the straight line between the previous and later waypoints of it didn't collide with any of the obstacles. Fairly simple but effective, this method makes the origin paths, which have 12 waypoints, reduced to 4 waypoints after the redundant waypoints are trimmed. Now, I will introduce our back-end trajectory optimization process. First, let's specify our optimization problem. Suppose we receive n waypoints from front-end planner. The whole trajectory is divided into n plus 1 subtrajectories. Our optimization object makes the trajectory begin with the initial states, passing through all the waypoints without collision, and finally reach the target states. Also, the whole trajectory should satisfy all the constraints. There are several constraints when optimizing the trajectories. Capital T is the maximum time for each subtrajectory. The velocity, acceleration, and control input, they all have their upper and lower bounds. As described above, besides the initial state and target state, we only constrain the position on each waypoint. However, for the continuity and smoothness of the whole trajectory, both state variable and control inputs cannot have sudden changes. Thus, the connection of two subtrajectories must have consistent state variable and control inputs. We also need to consider the constraints resulting from obstacles. The front-end algorithm generates waypoints from a collision-free path without considering kinodynamics. In the figure, the red dotted line shows a possible but not feasible trajectory based on two collision-free waypoints. We adapt a method called sailing corridor, an area including two waypoints of the current subtrajectory while excluding all the obstacles surrounding. The subtrajectory should be inside the corridor. We propose two different objective functions for the problem. First function aims to generate a fuel-saving trajectory. We know that two engines exert influence on fuel consumption directly, and control input torque are linear combination of the two forces generated by the engine. Thus, minimizing control input torque guarantees ASV sailing in an eco-friendly way along the output trajectory. Besides, the time factor should be taken into account. As we expect, ASV should consume less time while ensuring the task completed well. When smoothness becomes a major concern for trajectory planning, we should minimize acceleration object. The right side shows the optimization process pseudocode. In the experiment, we adopt Kingfisher robot as the ASV model and use gazebo as a simulation environment in this sector. Trapezoidal collocation is used as our optimization tool. The simulation environment contains 3 different obstacles in a 20 × 20 square meters task area as shown in figure. The generated trajectory by minimum control input function is demonstrated in the middle figure. 3 pink points demonstrate the location of 3 waypoints generated by the front-end planner. The green arrow sequence denotes the expected trajectory by the optimizer, and the blue one denotes the trajectory our model performs in the gazebo simulation environment. The detailed control variable and state variables are presented in the right figure. ASV tends to have a relatively large control input at the beginning of each subtrajectories and makes itself have a high surge velocities. This makes it saving fuel while maintaining relative high velocities. The generated trajectory using minimum acceleration function is demonstrated in this page. Since the optimizing objective changed to the acceleration, the curves of the velocities perform smoother and minimum control input. Furthermore, experiment trajectory tends to keep current velocities and reluctant to change directions. Finally, we compare our work with the methods presented in the previous work. The results shown in previous work performs relative low speed trajectory with an average speed of 0.26 meters per second. Though it managed to avoid obstacles in the environment, the trajectory shows that the ASV sails as the previous work just at the edge of the obstacles, which makes it dangerous in the real world. The closest distance between ASV and the nearest obstacles in our trajectories are 1.2 meters and 0.53 meters, respectively. It proves that our methods have more effectiveness and more security. That's all. Thanks for your attention, and please visit our website for more information.